I guess we'll move on to the next speaker, an excellent speaker. I'll be speaking myself about the urban stream syndrome. So I guess I'll give you a moment to pull up the PowerPoint. If we go then past the cover slide to slide 2, when we talk about urban stream syndrome, Tim also mentioned Chris Walsh is one of the earlier researchers who identified this really about 10 years ago. People started recognizing this, and it refers to a set of conditions related to the ecological degradation of streams and urban watersheds. And it's called a syndrome because there are many different attributes to it. So we're talking about changes in hydrology, stream geomorphology, pollutant loads, and stream ecology. So I'll do a brief overview of these different types of changes and talk about some of the studies that have been done. And then I'll finish with just talking a little bit about some of the solutions to this problem. So if we go to the next slide, slide 3, there's a Google Earth image here of relatively undeveloped watershed in Orange County here by Laguna Beach. And so to illustrate what the urban stream syndrome represents, imagine in this undeveloped watershed that you're a raindrop and you're falling on the middle of this slide here in the image, and that raindrop's going to hit vegetation, so some of it will attach to the vegetation, some of it will be broken up as it hits the ground, some of it will hit the ground directly, some of that will be absorbed. Eventually, if there's enough rain, it runs off a little bit and slowly builds up into some runoff that goes into the streams that are illustrated here. If we go to the next slide, what happens, this is not one of the low urbanization watersheds. This also is in Orange County and Costa Mesa, but this is a very high impervious surface. So what happens to most of the raindrops that are falling on this sort of landscape is that they're hitting most likely impervious surface, a rooftop or concrete, and they quickly run off into this network of storm drains that we've developed, and they accumulate very quickly. And so if we go to the next slide, on the effects of urbanization, there's a lot of effects, as I mentioned before, on the urban stream syndrome, but largely what we're interested in is what happens on the hydrology. And so what this illustrates here, if you go from the top left where it's not urbanized, it's natural ground cover, you see that a lot of the water actually evaporates or is transpired from the plants. Some of it infiltrates, and a relatively small amount is runoff. And as we move down to greater and greater urbanization, we have the next diagram over to the right shows 10 to 20% impervious surface. We're starting to get more runoff, and then down in the lower right we have 75 to 100% impervious surface. We still get evapotranspiration, not as much transpiration because there aren't so many plants, but we get a very high amount of runoff. So what this does is it changes the hydrograph so it's much flashier. And the other thing that's not so clear from these diagrams or from my sort of thought exercise of being a raindrop is that we get more dry weather flow also, so that urban water use runs off the landscape all year round, and particularly in places like Southern California where we have naturally a very long season without much rainfall, our streams are changed so that not so much that we have reduced base flow, but we actually have increased base flow during the dry weather. If we go to the next slide, this just illustrates the hydrograph and what the effects of urbanization are. So if we start at the top graph, we see the bars are the rainfall, and the line is the discharge in the stream. And so you see shortly after the rainfall, there's an increase in the discharge. It peaks. There's a lag time, but it peaks and then it drops away. And that's in a natural setting, natural landscape. After urbanization, on the bottom panel, you see that it's a much shorter lag time because the rain moves much more quickly into the streams, and it's also a much higher peak because much more gets into the stream rather than being absorbed or infiltrated, and then it drops off quickly too. So that's what we talk about when we're talking about a flashy hydrograph. So if we go to the next slide, so one of the consequences of that changes in hydrology, that's a very important consequence, is that we have changes on the stream geomorphology. This is a picture here from a stream in Orange County, Lower Oso Creek. And what we see here is, greatly increased erosion from the stream, an enlargement of the channels. So they're wider channels, incised channels. In this case, the incision is about 20 feet or so. And as a result of that incision, the stream is disconnected from the floodplain. So, that has a continued hydrologic consequence, but it also has really important ecological consequences because that connection between the stream and the floodplain is really critical for many organisms and for a lot of the functions the ecological functions that streams perform. So if you go to the next slide, slide 8 here, we have effects of urbanization on pollutant levels. And this is just a quick illustration from NRC report, but it just shows 3 different types of pollutants, TSS, so total suspended solids, total phosphorus, and zinc. And it has the levels of those pollutants in different sorts of land uses, and I've highlighted in green here the open space. And so in each of these cases, the pollutant level is lower in the open space than it is once the landscape gets urbanized. And then finally, the next slide, I want to talk about effects of urbanization on stream ecology. So the stream organisms are pretty interesting because since they're living in the stream, they're really tightly dependent on those physical and chemical conditions in the water. So we find that the organisms are keyed into the amount of water flow, various aspects of habitat quality, but in particular sedimentation can have a very big effect on the suitability of the habitat for different organisms, and then of course the water chemistry. And so what we find is with urbanization, we get changes to the organisms in response to those physical and chemical changes. We also, one of the consequences is get reductions in the number of native species in the stream. And then we also find increases in exotic species or invasive species in the stream. So in a few slides, I'll give you some examples of these. In the next slide, I just have one quick example. There's lots of examples of the changes in water chemistry, in particular in toxicity and effects on stream organisms. I just wanted to talk about this one study, which was published just this year, looking at the impacts of highway runoff on coho salmon. And so what this study did, the graphs show in 3 different years the rainfall, and then after a storm, these researchers collected the runoff, and they put adult salmon either in the highway runoff or clean well water. And what they were looking for is either mortality or what they call pre-spawn mortality syndrome. So that could be, it could be death, but it also could be lethargy, loss of orientation, or loss of equilibrium. And the results are really quite striking. You can see in the little legend, there's a jumping salmon that's asymptomatic, or a jumping salmon with an X through it, which is symptomatic or dead. And then for each of these collections, each bar, they're showing how many individual fish they had in each treatment, either the unexposed controls or the stormwater exposed treatment. And in every single case, when the fish were exposed to stormwater, they died or they had the symptoms of pre-spawn mortality syndrome. And in every case, when they were exposed to just the clean well water, they were asymptomatic. So this is a pretty dramatic example of the sorts of toxicity that can come when stormwater enters into the streams. I'm not going to talk about this, but this study is also especially interesting because after what the experiments that I show here, they passed the runoff through biofilters, and they found that it completely removed the toxicity to the salmon, and they became asymptomatic after the stormwater went through biofilters. But that's not my point today. Okay, so if we talk about the next slide, one of the critical things about the urban stream syndrome is that not only do we see these effects that I talked about, but especially these biological effects are occurring at very low levels of urbanization. I would say surprisingly low levels. I think if you think about the amount of development in a watershed that represents 2% or 10% of impervious area, it's not a lot of development, but what we find is that we are seeing these thresholds in effects at those sorts of urbanization levels. So it's different in different watersheds and in different populations. There are different sorts of thresholds, but they're often in the 10 to 15% range for fish, and invertebrates they're even more sensitive, so it can be at as low as 1 or 2% of impervious surface cover. And the graph just gives an illustration of this from some work that was done in Washington, and you can see the stippled bars are where the habitat was in excellent condition, and the hatched bars are in degraded condition. There's a pretty quick switch from excellent to degraded right around 10% or so. So if we go to the next slide, what I want to talk about now is just some examples of what we've seen here in Southern California. And this first example is about stream communities in the Santa Monica Mountains. And the researchers were really focusing mainly on amphibians. And on the left side here, we've got a set of native amphibians. We've got a salamander and a tree frog and a toad. And then on the right side, we have introduced species, so introduced crayfish, bullfrog, and mosquito fish. So if we go to the next slide, we see that typical for the urban stream syndrome, we see changes to the physical habitat. I thought it might be interesting to look at sort of what those changes look like. On the right, there's just a sketch, a diagram of what a natural stream would look like with the 3 different habitat types that we generally recognize in streams, so riffles, pools, and runs. And so what you see on the left is that there's a lot of riffles. There are quite a few pools in these streams, and then there are some sections of runs. When we look on the right at what the habitat distribution looks like in urban streams, what we see is fewer pools and many fewer riffles and a lot of runs. So the run would be just a smooth section where the water is flowing relatively quickly. And so what it means is that there's a lot less habitat diversity in the urbanized streams, and there's also a higher water flow and increased water depth. And then, as I mentioned before, we've also found that the streams become much more permanent. So that's illustrated in the table below, which just talks about or shows the length of dry stream in urban versus natural. And so you can see that there's much less dry stream in the urban areas than there are in the natural areas. So next slide. So that has consequences on the species. So there's many different ways that we can look at this, but in streams, when we're interested in stream health, we often look at the invertebrate taxa, and there are some groups that are known to be sensitive to pollution and other sorts of disturbances. And probably the most popular group to look at are these EPT taxa, Ephemeroptera, Plecoptera, and Trichoptera. And so what this graph shows is a plot of the percent of all the invertebrates that were sensitive EPT species plotted against the amount of urbanization in the watershed. And what we see is at the lower levels of urbanization, we get high percentages of all the inverts are these sensitive species. But as soon as we get to about 8% urbanization, those EPT taxa drop out. And so this is another example of the threshold where we start seeing the urban stream syndrome. In this case, it's about 8% for these species. And if we go to the next slide, there's also, along with that, not only do we lose some of the native species, but we pick up introduced species. And so in this is just a listing of the streams that were studied in this Riley et al. Study, and above the line are the natural streams and below the line are the urban streams. And then in the columns are different species. On the left it's the native species, and on the right introduced species. And so what we see is there are some species, this Hyloregilla, the HYRE species, that's a very cosmopolitan species. They occur in all the streams. But there are other native species, this other tree frog and the California newt, which are basically only occurring in the natural streams. And conversely, we look at these introduced species, the crayfish and the bullfrog and exotic fishes, and we see that they almost exclusively occur in the urban streams. And so the physical and chemical changes that happen as a consequence of urbanization are both bad for native species, but it also turns out that they're good for the introduced species. And those introduced species can have a big effect on the ecosystem health, the way that the ecosystem functions. Okay, so if we go to the next slide, I have one other example here, this time from Australia. I wanted to have some global diversity in here, and this is from a study that was done around Sydney. And again, this study looked at macroinvertebrates as an indication of the health of the streams, the stream ecosystems. And what the plot shows here is the number of different sites of 3 different habitats. They looked at edge habitats, riffle habitats, and pools. So some of the same habitats I showed in the earlier slide. And you can see they had a lot of reference sites where there was less than 2% imperviousness, and then they had a number of sites that went from between 2 to 10% all the way up to 45% impervious, and those were their urban sites. And in this case, they're using 2% as that threshold for connected imperviousness. So if we go to the next slide, we see the results of this. And again, these are invertebrates that they're looking at. There's a number of different aspects of the invertebrate community that they're looking at. They're looking at total richness. The signal per habitat, signal is just a bioassessment index that they have calculated. And then on the bottom graph is our old friend, the EPT richness per habitat. And what you see in each case is that the urban streams consistently have lower whatever that index is that's showing the health or reflecting the health of the stream. So either lower richness, lower signal values, or lower EPT richness per habitat. And in addition, one of the things that they found here was that there was a lot more variation in the natural streams that were naturally vegetated than there was in the urban waterways. And so I think that reflects the homogenization of the habitat that we see when we get urbanization, and that's part of what brings in the introduced species, the exotic species. Okay, so that's a quick summary of some of the symptoms of the urban stream syndrome. And so what I want to do is just spend a very short time talking about possible solutions. The first one, and this is sort of the obvious way to think about if you've got a problem in the stream, especially if it's something like stream geomorphology where you've had either the incision or a disconnection from the floodplain. It seems like the most obvious solution might be to do an in-stream restoration, and we can restore stream geomorphology. We can increase the heterogeneity in stream habitats. We can make a stream that's in size be connected to a floodplain again. So these are all things that can be engineered and are possible. But they're really not the solution, at least not a sustainable solution to this urban stream syndrome, because it just doesn't address the root problem that's causing the decline in the stream ecology and in those physical and chemical conditions. So if we go to the next slide, we have sustainable solutions. So, these solutions fall under lots of different labels. We've got low impact development or water-wise urban design, green infrastructure, green streets, all those sorts of categories. But all of them have in common this idea that we need to disconnect stormwater runoff from the storm drains. We need to minimize the effect of imperviousness, and that's really the way to have a sustainable solution to this. So there's many different approaches. We've heard about some of those already, and we'll hear more in the future, but those would include things like stormwater detention basins, or we could use permeable pavement, or stormwater biofilters like rain gardens and bioswales. And then Tim just talked about the Little Stringy Bark Creek project, and this is, ultimately is really the direction that we should be aiming for. That would be our aspiration, I think, where you can actually restore a watershed by a network of biofilters or other LID techniques that could reduce the excess water flow and pollutants to the streams and allow the stream fauna and flora to recover. And that's most likely to be successful in watersheds that have relatively low impervious surface cover now. But even in urban watersheds, there can be a benefit, as we just talked about. It can be, we may not be able to get it back to natural hydrology. We may not be able to get all of the species back either, but we can improve the stream conditions, and there's also these other co-benefits in terms of reducing pollutant loads to receiving waters, but also other sorts of ecosystem services that both in terms of sort of biological services, but also cultural, aesthetic services that could be a benefit of these sorts of watershed restorations. And not very many attempts to restore entire watersheds so far, but we're definitely moving in that direction. And so, in conclusion, there's a lot of aspects to the urban stream syndrome, but it's really driven by changes in hydrology due to urbanization and especially the increase of impervious surfaces. And there are very extensive effects on stream ecology, reductions in native biodiversity or increases in introduced species. The effects are seen at a relatively low degree of urbanization, 2 to 15%, and they can be pretty dramatic effects even at that low amount of urbanization. And then finally, the sustainable solution has to be based on restoring hydrologic function. And that's it. So, any questions?
Yeah.
Yeah, hi, Perry.
Hi. Yeah, it was a great talk, thanks. Is there any demonstration projects or push for projects like Stringy Bark Creek?
Yeah, so a little bit, and I think we're definitely moving in that direction, but I still think Little Stringy Bark Creek is sort of a global model. And if you think about how much work it's been to accomplish that, I guess you can get a feeling for why it's not done in more places. That's why I think what Tim was saying about using it as a model, I think that's really true. I think as people recognize that it is feasible, then it's possible that they will be inspired by that. Now, having said that, there are definitely efforts to do something like that in Los Angeles and in other places, but for us it's driven by regulations that ultimately are trying to protect the ecology, but in the proximate, they're trying to reduce pollutant loads to receiving waters. And so we have, we have under the Clean Water Act, we've got regulations that that dischargers have to pay attention to. And that's been going on for a long time, but more recently, the dischargers have been viewed as being cities that have impervious surface. And so they're not actually, it's not a pipe, but it's viewed as a discharge. And so here in the Los Angeles area, for example, right now, all the watersheds, all the municipalities have formed into groups that have been producing enhanced watershed management plans, and those plans include a network of LID techniques. So it's much more urbanized than Little Stringy Bark Creek, and so it's not going to restore the watershed really, but it's going to really provide this network that it's driven not so much just because people want to do it, but because they're required by the law to do it.
Yeah, thanks.
Oh, we can't hear you, Stan.
Great talk and great introduction to the talk that I'm going to do as well. Right. I guess one thing I was going to clarify is this issue of what happens to base flow during urbanization. And I think that the answer is that it's very location specific. So of course in Southern California, as you rightly pointed out, we've actually experienced enormous increases in base flow with urbanization. There was a paper that came out in Geophysical Research Letters that looked at historical stream flow, for example, in the Los Angeles River. I think that the number was 500% increase over the last 100 years, something like that. So enormous increase in base flow. But I guess what I have come to understand from working with my colleagues in Australia is that we're fairly unusual, and we're unusual in the sense that we import so much water. So that increase in base flow is actually a symptom of massive interbasin water transfers.
Right.
Then in watersheds which do not have interbasin water transfers, more typically the pattern is with increasing urbanization, the base flow actually declines.
Yeah.
So I didn't realize this until I started interacting with all of my colleagues, because I thought this was the norm, but in fact I guess we may be a bit of an outlier because of all of the water we import.
Yeah, I think that's exactly right, yeah.
I did have a question too. I really loved your examples, and I thought the habitat shift, the decrease in diversity of riffle pool habitat was particularly interesting. And I wanted to know, I haven't read that paper, I definitely want to read it. The increase in the runs, is that concrete lining? Or is that a sort of a earthen stream which is just becoming less, less diverse in habitat?
Right. So there definitely are some concrete lined streams in this area, and that obviously just destroys the habitat heterogeneity. There's nothing, right? But that's not the case in those streams. Those streams are still natural bottom streams. It's just that presumably it's the hydrology, but it could be excess sedimentation. Something has reduced the heterogeneity in the streams, so that even though I know a lot of those streams because it's in my area, and so even if you know what stream they're talking about, you would not necessarily think that this was an impacted stream. You would not think that it was channelized or anything like that, because it's not. So it's actually a consequence of the urbanization. But if you went to the stream, unless you measured those things, you would not know that it had been altered that way, just to look at it. So another type of alteration that didn't talk about at all, but now that you're talking about, sort of Southern California specific things, is changes in vegetation. And so in our streams, we don't worry so much about changes in vegetation. We definitely have riparian trees that are a part of the stream community, but people aren't as concerned about the loss of those trees. But if you go up to the Pacific Northwest or even Northern California, where we have salmonids, then the temperature increase is a huge impact on the salmon. And so in some places that are one of the consequences of urbanization is actually having the removal of the trees. And then again, the stream could look exactly the same. And in fact, in that case, even if the habitats look the same, the habitat diversity, it's that change in the physical characteristic, the temperature, that completely destroys the quality of the stream for the salmonids.